There is a story about Albert Einstein's first trip to the city of Copenhagen in the summer of 1922. It was after he had received the Nobel Prize, a thing delayed by preferences, politics, and more than just a bit of anti-Semitism, and he was on his way home to Berlin from Oslo after having given an acceptance speech for the award at a Swedish conference there, with King Gustav V in attendance. The purpose of his stop in the city was to visit his colleague and friend, Niels Bohr, and to see Bohr's Institute and talk a bit of shop. When he got off the boat that had ferried him across the narrow expanse of water there in the Baltic Sea, Bohr was waiting for him, and after exchanging pleasantries, the two men boarded a streetcar to take them from the port down to the part of the city where both the university and Bohr's Institute were to be found. However, as would so often be the case when the two men got together, they soon fell into a deep discussion regarding the nature of quantum mechanics and its emerging implications for physics. So engrossed were they in their back and forth that they missed the stop for the university and rode the line out to near its far end before realizing that they had so overshot their mark. Unfazed by the air and still engaged in conversation, they just decided to ride the car back into town on its return trip. But once again, they missed their place to get off because of their discussion. While neither man was exactly clear in their later reflections as to how many times this took place, it seems that the streetcar conversation required them to take more than a few round trips, something Bohr noted by saying, quote, "We rode to and fro, and I can well imagine what the people thought about us," end quote. Bohr and Einstein were interesting in that they would receive sequential Nobel Prizes that were given actually in that same year of 1922, each for their work on light quanta as they applied to physical systems, and for many years their works and thoughts, like two particles bound together in a quantum state, would be entangled. Often at odds intellectually and philosophically, they were extremely fond of each other, and their relationship would weather the storms of war, political disagreement, and separation to remain strong and productive. Nowhere was this more true than at the 1927 Solvay Conference, where the two men would find themselves dueling over one of Einstein's most ingenious thought experiments. This time on the Scientific Odyssey, we'll explore Einstein's relationship with quantum physics, as well as Niels Bohr, as he struggled to come to terms with the idea that physics might not be what he thought it was. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a mini-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 3, Finding Our Place. Episode 50.9, Supplemental, Albert Einstein, Entanglement. By the year 1921, physics had a problem on its hands. And when I say physics, what I really mean is the broad social apparatus of physics that recognized scientific accomplishment and progress. That problem was the growing embarrassment of Albert Einstein not having been awarded a Nobel Prize for his work, either in 1905 or in the years after, up to and including the 1915 development of general relativity. Now, the root of this difficulty lay in the statement that Alfred Nobel had made in establishing the prize, that it should go to the, quote, most important discovery or invention, end quote, made in the field in recent years. This meant that there was, and to a degree, by the way, still remains, a bias towards experimental, or at least experimentally confirmed results, as opposed to those founded on theoretical principles. For that reason, the committee that makes the decision of which nominees for the prize shall be awarded a given year's recognition was, and still is to a degree, skewed towards having more experimentalists recognized than theorists. Einstein was first nominated for the prize in 1910 by Wilhelm Oswald, who had once ignored Einstein and his father's pleas for an assistantship about a decade earlier. Oswald had been one of those anti-atomic theory chemists who had been swayed to drop his objections to the theory based on Einstein's 1905 paper on Brownian motion. As impressed as he had been by that piece of work, he recognized the truly revolutionary nature of special relativity, and so he nominated Einstein on the basis of that work. Unfortunately, the Swedish selection committee was less impressed by the lack of experimental verification of Einstein's ideas, and so he was passed over in that year and in each year thereafter. Even after the theory was generalized to include gravitation and accelerated reference frames, so that it was able to explain things like the precession of Mercury's orbit, the committee demurred, sticking to its preference to favor experimental work. And to be clear, Einstein was not the only one who suffered from this inherent bias. Max Planck, whose solution of the ultraviolet catastrophe initiated the quantum revolution, was not awarded a Nobel Prize until 1919, and even then it was a tricky decision, with his award actually being the delayed 1918 prize, as the committee had been unable to resolve a deadlock in its deliberations in that earlier year. Things, however, really came to a head with Eddington's results in 1919, and it seems like the committee would have little choice but to award the prize to Einstein for his work in relativity after that point. Except that it was in that year and the years after that politics and anti-Semitism really stepped in to continue delaying the award. In 1920, 6 prominent physicists, including Hendrik Lorentz, stepped forward to nominate Einstein for the prize. But by this point, 2 individuals who we mentioned in our last episode, Ernst Gerke and Philipp Lenard, were lobbying behind the scenes to keep the prize from being awarded to Einstein. They put forward the same inaccurate arguments that had been used at the nationalist rallies in Berlin earlier that year, and with some effects. In a 7-page memo drafted by the committee chair, Svante Arrhenius, regarding the reasons for not awarding that year's prize to Einstein, one can clearly detect both of those men's arguments weighing into the decision. For Einstein, the failure to win the prize seems to have pushed him to a position of thinking that the committee and the process was more or less rigged against him. As it's so often been the case when he ran up against short-sighted authority, he washed his hands of the whole thing and moved on with sort of a bemused fatalism. The prize that year actually went to the director of the International Bureau of Weights and Measures for his work in developing alloys of metal that were less susceptible to change due to environmental conditions. Important work to be sure, but not exactly something anyone would have called groundbreaking. In 1921, the swell in support of Einstein only grew, as in that particular year now there were 14 different researchers who nominated him, including the recent prize winner Planck and Eddington, whose observations, of course, had proven the general theory's validity. Once again, the Nobel Prize Committee bungled the job by assigning sort of the task of preparing a report on the validity of the nominations to an ophthalmologist whose grasp of the relevant mathematics and physics was nearly non-existent, and who found the idea that the lengths of things in moving reference frames could change absolutely horrifying, as he wrongly assumed that it might invalidate his profession's need for highly precise measurements to make eyeglasses and other assorted optical devices. The 50-page document he prepared reads as if it had been written by Einstein's opponents and detractors. As a result, the committee sort of locked up again, just as it had done back in 1918, and it chose not to award a Nobel Prize in Physics for the year of 1921. At this point, though, the prestige of, the whole Nobel apparatus was now being called into question. In the broad scientific community, outside of those German nationalists who were working to undermine Einstein on account of his Jewish heritage, there was a growing feeling that Einstein's lack of an award reflected much more prominently on the Nobel Committee than it did on Einstein. In other words, everybody knew that he deserved one of these things, that his work was by far and away the most notable that had been done in the last 20 years. And the Nobel Committee's lack of recognition really meant that they were out of touch. Every year that the committee failed to recognize what was so obvious to nearly everyone was an indication that perhaps the process was no longer valid and should be seen as being less prestigious than other awards such as those being given by the Royal Society. As Lorentz had written in his nominating letter, Einstein had, quote, placed himself in the first rank of physicists of all time. To not recognize that said something about the Nobel Committee. The impasse was finally broken in 1922 when a theorist from the University of Uppsala, Carl Wilhelm Ussing, joined the Nobel Committee. He could see that the deadlock was actually, a huge problem, and then he had this insight to recognize that the sticking point had actually become this theory of relativity. If he could find a way to get around that, maybe some progress could be made. So what he suggested was that the committee award Einstein the 1921 prize on the basis of his explanation of the photoelectric effect, the application of the light quanta ideas put forward in his 1905 heuristic paper. The solution had the advantage that it built on the 1918 prize awarded to Planck, and it could be given in conjunction with the 1922 prize that would be awarded to Niels Bohr for his application of quantum principles to explain emission and absorption spectra of hydrogen atoms, which also use light quanta. Moreover, by phrasing the suggestion that the prize be given for, quote, the discovery of the law of the photoelectric effect, end quote, Ussing's proposal circumvented the bias against theoretical work, which, of course, had formed the bulk of the paper in which the explanation had been given as an application. It really was a fine bit of irony. But, irony or not, Ussing's ploy did in fact carry the day, even over Lenard's strenuous objections. But which, by the way, one can kind of imagine how much it would have galled Lenard that the man with whom he now had such a bitter rivalry and so much enmity towards was going to win physics' most prestigious prize on account of explaining a phenomena he had first observed and documented and had also been awarded a Nobel for. In Walter Isaacson's words, quote, so Lenard was doubly outraged that, despite his opposition, Einstein had won the prize, and worse yet, done so in a field that Lenard pioneered. He wrote an angry letter to the Academy, the only official protest it received, in which he said that Einstein misunderstood the true nature of light and was, in addition, a publicity-seeking Jew whose approach was alien to the true spirit of German physics, end quote. For his part, Einstein was not available to receive the prize at that year's official awards ceremony. Burned so often by the committee's intransigence and deciding that he had better things to do than wait around for a bunch of Swedish know-nothings to once again misunderstand his work, he had booked a tour of Japan, Southeast Asia, and Israel, once again combining scientific outreach and fundraising for a future Hebrew university that took him out of Europe for those dates. As had been the case in the United States, the tour was an enormous success, and it would be the only time in his life that Einstein would visit the Levant. Even after the founding of Israel, he understood that to move to the reason, something that he would later say his heart moved him to do, would mean the end of his life as a private person. And so it was that reason, as he put it, told him no. Back in Sweden, the awards citation and award speech, given by Arrhenius, encapsulated the tension that had long been part of the controversy as well as its resolution. The citation for the award read in part, quote, for his services to theoretical physics, and especially for his discovery of the law of the photoelectric effect, end quote, and then added, quote, without taking into account the value that will be accorded your relativity and gravitation theories after these are confirmed in the future, end quote. Arrhenius would say in front of the gathered luminaries of that year's presentation ceremony, before handing the award to the German ambassador to Sweden, quote, there is probably no physicist living today whose name has become so widely known as that of Albert Einstein. Most discussion centers on his theory of relativity. This pertains essentially to epistemology and has therefore been the subject of lively debate in philosophical circles." End quote. In these words, he acknowledged the difficulties the committee had had without actually acknowledging the difficulties the committee had really had, but then went on in the resolution to say, quote, "Einstein's law of the photoelectric effect has been extremely rigorously tested by the American Millikan and his pupils, and passed the test brilliantly. Einstein's law has become the basis of quantitative photochemistry in the same way as Faraday's law is the basis of electrochemistry." End quote. And so it was that in this way, the Nobel Prize Committee was able to sort of cover itself without having to make the various changes that, well, down the road Einstein's would actually make so very necessary in how the committee considered awarding prizes. As he promised, Einstein gave part of the financial portion of the award to Mileva for her upkeep and used the rest to establish a trust, the interest of which was paid out to his two sons. Another note of historical interest is that the man whose work had established relativity, Arthur Eddington, never received a Nobel Prize for his efforts, a somewhat stunning oversight if you ask me. In fact, no award would be given that was directly related to the theory of relativity, though, as we've mentioned before, the 1984 prize was awarded for the indirect observation of gravitational waves in the decaying orbits of neutron stars, and the 2007 prize was awarded to the three principal investigators of the LIGO project for their work that led to the direct detection of those same gravitational waves. So, it is at this point that we come to one of the most consequential friendships in the history of science, that between Einstein and Niels Bohr. As a bit of background, we did an episode on Bohr back in our History on the Atoms series, as well as 2 episodes on the long debate between the two men regarding the interpretation of quantum mechanics that was as much philosophical as it was scientific. Now, you don't need to go back and listen to those before continuing here, as we'll cover the relevant details as needed, but if you want more context on the life of Bohr and his interaction with Einstein, I suggest you give those a listen. So, just a little bit about Bohr. He had grown up in Copenhagen and was a member of an upper-middle-class family of intellectuals. He was handsome in his own fashion and quite an athlete, playing goalie for the Danish Olympic soccer team. After receiving his PhD in physics, he married his sweetheart, who came from an old noble family, and it was one of those fairy tale weddings with the beautiful cultured bride and the dashing and intelligent husband that sort of captivated the whole nation. Bohr then went off to do postdoctoral work in England, starting first at Cambridge, but then moving to work with Ernest Rutherford at the University of Manchester, just as Rutherford's team there, led by Geiger, was putting together the nuclear model of the atom that showed that the electrons in an atom orbited a small, dense, positive nucleus. The problem with the model was that Rutherford's team couldn't explain how the electrons avoided spiraling into the nucleus, something required by the laws of classical electrodynamics. In 1913, Bohr, now back in Copenhagen, developed a model of electron orbital energy levels that explained why the hydrogen atom created the spectrum it did. It really was a masterpiece of theoretical physics, explaining the observations of Kirchhoff and Bunsen, and it catapulted Bohr to instant status in the developing community of those who focused on theory. In his model, Bohr said that electrons can only exist at very specific energy levels, something we've discussed in our episode in this series on light, and that it transitioned from one energy level to another instantaneously only through either the absorption of a quantum of light with an energy that was exactly the same as the energy difference between the two orbitals, or by emitting a quantum of light to transition quote-unquote down from a higher or more energetic energy level to a lower one. In this explanation, he explicitly used Einstein's ideas on light quanta, not as artifacts of how light is absorbed or emitted by matter, but instead as actually being the way light actually is. The theory was something that Einstein would later tell a colleague that he'd actually considered in some time after 1911, but had not dared to publish as it seemed too speculative. Hence, he was deeply impressed and envious in the way one sometimes thinks, why didn't I do that? Why didn't I come up with that idea? By Bohr's willingness to follow the whole theory from initial conception all the way through to the conclusion, even when it seemed well outside the accepted ideas related to emission and absorption of light by matter. Einstein would take Bohr's work and follow up on it by publishing a series of papers in 1916, shortly after his seminal work on general relativity. And that work sort of culminated in a summary of ideas in a 1917 paper titled, quote, A Quantum Theory of Radiation, end quote. In this, Einstein combined Bohr's model with Planck's theory to derive a fairly simple and straightforward way of developing the spectrum of a blackbody. So profound was this result that Einstein would write his friend Michele Besso and say, quote, A brilliant idea dawned on me about radiation absorption and emission. It will interest you. An astonishingly simple derivation, I should say the derivation of Planck's formula, a thoroughly quantized affair, end quote. It would be from this work that Einstein would imagine a way to create light emission in a gas that was stimulated by the passage of another light quanta of the same frequency. This stimulated emission would not only be a photon of the same frequency, but the waves of the two would be coherent, or quote-unquote sort of what we might call in sync, as it were. Each light quanta or photon would be able to stimulate emission of another photon from another atom with an electron in that same excited state in the gas if everything was kept in the right conditions. And if that were the case, if you had a gas in a chamber, that chamber would be able to produce a beam of light made of photons, all having the same frequency, or at least, or I shouldn't say at least, but of being the same color and traveling coherently in the same direction. This, of course, is now known as light amplification by stimulated emission of radiation, or more commonly, the laser, a technology Einstein would be the first to theorize about, which would then later be developed in the years after World War II until the first working examples were developed in the early 1960s. Another thing that Einstein learned as part of this work was that he had to deal with the idea that since these photons behaved as if they had particle nature, they would be emitted in a specific direction as opposed to traveling outward from an atom in all directions, or omnidirectionally as you'll sometimes hear it called, as would be the case if light were actually a wave. The thing that was different then, and the thing that was really difficult, was in actually determining which direction the emission of that sort of particle of light would take place out of the atom. And it turned out that to make that work, Einstein had to assume that that would be a probabilistic process, the direction in which that photon of light came out of the atom. This would start Einstein, and really in a sense all of physics, down a long and troubling path that said that atomic and subatomic processes were not deterministic in behavior, but actually pretty much completely statistical. Over time, this would come to bother Einstein a great deal, but that's a bridge we'll cross here in just a little bit. In 1920, after years of reading each other's papers in the various journals and being unable to travel because of the Great War, Bohr finally got to Berlin and was able to meet Einstein in person. By this time, Bohr's institute was up and running, and he was in deep collaboration with Arnold Sommerfeld at the University of Munich and Max Born at Göttingen to develop a fully what we might call a semi-classical quantum orbital system for the electron's motion around the nucleus of an atom. The Copenhagen-Munich-Göttingen triangle, as I like to call it, would, with important contributions from Cambridge, become the center of research in theoretical quantum physics. As for the meeting, Bohr showed up at Einstein's apartment bearing gifts of Danish cheese and butter, true luxuries at that time in Berlin, and the two almost immediately launched into a wide-ranging discussion regarding the implications of Bohr's ideas regarding quantum mechanics, ideas Einstein found very uncomfortable, in that they seem to undermine one of the most cherished pillars of physics, that idea that we've already mentioned of determinism. And before we go any further in that vein, I should note that while Einstein may have had qualms about the subject matter of their conversation, he had no such reservations towards Bohr himself. As he would write in a letter to Bohr a few days after that first meeting, quote, "Not often in life has a human being caused me such joy by his mere presence as you did." And he added to that, he took picturing your cheerful, boyish face, end quote. To his friend and colleague Aaron Fest, he wrote, quote, "Bohr was here, and I am just as keen on him as you are. He is an extremely sensitive lad and moves around in this world as if in a trance." End quote. For his part, Bohr revered Einstein and was often in awe of his intellect. When, in 1922, the two were awarded Nobel Prizes in physics, Einstein receiving that, of course, delayed 1921 prize and Bohr the 22 award, Bohr wrote of his joy that Einstein was receiving the earlier prize and thus first honored due to, quote, "the fundamental contribution that you made to the special field in which I am now working." End quote. In other words, no matter how much these two gentlemen disagreed with each other on the nature of things in physics, they were always tremendously close to each other personally. When Einstein returned from his overseas trip that we talked about in that opening part of the episode, and he gave his acceptance address in the summer of 1922, he stopped off in Copenhagen on his way home, and it was there that the two of them rode the streetcar back and forth, missing their stops as they became so engrossed in the discussion. It would be on that trip that the two of them would take up in earnest the debate as to the nature of quantum probability, and in doing so, their thoughts on the matter were to become, to use the quantum term, deeply entangled. No matter where they were, they would carry on a long and sometimes fierce debate on the topic. And yet, while the arguments and positions could be strongly held and presented, the two men never allowed this to become acrimonious. Instead, they so enjoyed each other's company and intellect that they would, for the next 30 or more years, make time to visit and even take sabbaticals in such a way as to be able to continue this conversation. So what was it about quantum mechanics that so bothered Einstein? While we talked about quantum theory in some detail over several episodes in our History of the Atom series, let me summarize a few of the major points here. First, on the scale of the microscopic, things don't behave continuously in the way we tend to experience them here on the macroscopic, sort of real-world scale. Instead, phenomena are quantized or discrete. Light comes in bundles of energy. Electron energy levels in atoms happen in steps like on a ladder. Physical properties like angular momentum come in discrete bundles. Now, by and large, Einstein doesn't seem to have had much of a problem with any of this per se. The second thing we might say about quantum theory is that many things in nature at the microscopic level display a certain type of duality. In the case of matter, all matter displays wave properties when that is what an observer tries to look for, and particle properties when that's what the observer is trying to look for. This is known as wave-particle duality, and that's what Einstein had argued for in his 1909 and 1911 presentations at major physics conferences. While he couldn't see a way around this reality, he was uncomfortable with this for a variety of reasons, as it seemed to call into question the philosophical position of what is known as determinism. As we discussed a moment ago regarding photon emission, if one embraced the picture that seemed to be emerging in the early 1920s, there was a real question as to how one determined what direction the photon was emitted in, and if the photon behaved like a particle, why did one see wave phenomena having to do with that particle? How does something act both like a particle and a wave? Well, the first indicated that there had to be probabilities involved, at least in terms of the calculations. And this was a problem for the idea of determinism. Determinism, at least in this context, is that all of the motions of things can be determined by an object's initial conditions and its interactions with other things. In other words, if you want to know where an electron is going to be at a given time, for example, what you could do is measure where that electron was at a certain point and how fast it was going at that time, and then characterize anything it might interact with, say an external electric field or another electron. Then one could do some mathematical modeling, calculations, that sort of thing, and you could come up with an answer for where the electron would be in the future. So what's the problem? Well, as Einstein knew and had spent his entire career working with, oftentimes systems with lots of particles couldn't actually be determined, as it were. That's where the statistical techniques that James Clerk Maxwell and Ludwig Boltzmann had pioneered had come in really in handy. Einstein had used those to great effect not only in the two 1905 papers, but in all of his work on light quanta up through about 1920. The philosophical problem was that there was a question as to whether the use of those tools for photon emission from atoms in a gas like hydrogen was just a tool to understand what was going on in large numbers of particles, too many particles to actually do the calculations for each individual particle separately, or if that statistical nature actually said something about the property of the emission process that made it actually probabilistic, which is something that Bohr was arguing. Over the course of the next decade, an answer would emerge that Einstein didn't much care for. As the Bohr-Sommerfeld semi-classical, semi-quantum model of the atom and the model of the electron behavior around the atom began to really break down in about 1922-1923, there soon came a flood of new research that made it very clear that Bohr's picture had a lot to recommend it. Now, what I mean here when I say Bohr's picture is really that Bohr's description of processes on the microscopic scale being governed by probabilities. A great example of this is probably radioactive decay. Let's say you have an atom that's radioactive. Say you have a uranium-235 atom. And what we know about uranium-235 is it has something we call a half-life that's about 4.5 billion years. Well, what that means is that in 4.5 billion years, a single uranium-235 atom has about a 50-50 chance of decaying into a different kind of atom, spitting out what we call an alpha particle and changing into a new type of atom or new type of element. Now, the thing that's really interesting is that coin flip of a chance that that atom has, Bohr argues that's a real thing, that there's really just a probability. Now, if you get to lots and lots and lots of atoms, right, let's say we get to, say, a mole of uranium atoms, so, 10 times, or 10 to the 26 power uranium atoms. Well, once you do something like that, well, what that means is that, after 4.5 billion years, half of the atoms will have decayed and half of the atoms won't. Now, you won't know which particular atoms will or won't have decayed, but that's how the probability works. Now, that's something that Bohr really strongly believed was a feature, an actual thing sort of baked into the reality of nature on that subatomic level. And Einstein was really uncomfortable with this. So what were the results that sort of came to support that kind of picture? Well, the first result was in about 1924. And it was Louis de Broglie's PhD dissertation that showed that electrons also displayed wave-particle duality, something that explained, by the way, why Bohr's energy levels were where they were in any given atom. Then, in 1925, the Austrian physicist Erwin Schrödinger generalized and extended what is known as the Hamiltonian formalism of classical systems so that it applied to systems that showed quantum behavior, and showed that the wave functions that came out of those equations could be used to describe electron behavior. In other words, he's able to sort of derive de Broglie's equations in a more general form. The problem here was that it was soon shown that Schrödinger's waves didn't actually describe the motion of electrons in an atom, but rather something else. And so it was that soon after the publication of Schrödinger's papers, Einstein's colleagues Max Born showed that the wave actually was something related to the probability of the electron's position, not the actual motion of the electron itself. In 1926, Werner Heisenberg developed a completely probabilistic description of electron absorption and emission that was soon generalized by Cambridge's Paul Dirac. Heisenberg then followed this up with his famous uncertainty or indeterminacy principle, depends on how you translate the German word, that showed very clearly that for microscopic phenomena, determinism was not actually the correct way to describe their behavior. From all of this was developed what is now known as the Copenhagen interpretation of quantum mechanics, which enshrined probabilistic processes as a fundamental part of quantum theory. Now, if you want to know more about all of this, beyond this very, very brief outline, you can go back to our History on the Atom series, or History of the Atom series, and listen to those episodes where we talk about that, which sort of run from about 2.13 to about 2.18, as well as a couple of supplemental episodes after 2.25 to get a fuller sense of all of the developments that we've discussed here. For Einstein, this shift from a picture of physics that was deterministic to one that was rooted in a deep understanding that subatomic processes were governed by laws of nature that included probability was just a bridge too far in a sense. What was really ironic about this was that those that created this picture of understanding and describing quantum processes used the very tools that Einstein had first pioneered in his 1905 paper on special relativity. As we mentioned in a previous episode, Einstein had spent a lot of time reading the work of Ernst Mach on the philosophical position that is now known as instrumentalism. He had not only accepted that position, but insisted that if something could not be observed in nature, then its inclusion in a descriptive theory was only being really used as a tool or an instrument to account for the observations that could be made and didn't necessarily have any sort of reality beyond that. And this is what had allowed Einstein to jettison the ideas of absolute space and time that led him to his first, insights and breakthroughs in special relativity. Now, at the time and in the years following, Einstein had had to fight against the old guard of physics that had sort of been trained in the assumptions of Newtonian mechanics. But as the evidence for his ideas grew, especially after the publication of the general theory, much of that opposition, though certainly not all of it, would fade. The next generation of theoretical physicists, most notably Wolfgang Pauli and Werner Heisenberg, were trained in a post-1905 curriculum, and thus the ideas of instrumentalism and the questioning of the older assumptions of classical physics were part of the story of being a great physicist. Einstein had done it. To a degree, Rutherford had done it. To a somewhat lesser degree, Bohr had done it. And so these young guns were more able to sort of accept that that's what they were going to have to do. And so they were able to reimagine what was and wasn't going on the scale of the atom or smaller, using many of the same intellectual tools that Einstein had pioneered that generation earlier. Only this time, it was Einstein that was in the old guard pushing back against their new description of processes guided by probabilities. There are a couple of humorous stories about this struggle in how it relates to Einstein. One involved Heisenberg's first visit to meet the great physicist. The two had corresponded about Heisenberg's uncertainty principle and had not really resolved much when the younger man visited Berlin to give a talk. Einstein invited his young colleague around to continue the conversation at his apartments, and Heisenberg graciously accepted. The conversation was, of course, as genial as always, but one part of the exchange is reported to have gone as follows. Quote, "We cannot observe electron orbits inside the atom," Heisenberg is said to have claimed. "A good theory must be based on directly observable magnitudes." Einstein replied in protest to this. He said, "But you don't seriously believe that none but the observable magnitudes must go into a physical theory?" To which Heisenberg responded, "Isn't that precisely what you have done with relativity?" At this point, I just love Einstein's response. Possibly, I did use this kind of reasoning, but it is nonsense all the same. End quote. And in a conversation with his friend and colleague, Philip Frank, while visiting Prague, there's this complaint that Einstein makes. He says, "A new fashion has arisen, in physics, which declares that certain things cannot be observed and therefore should not be ascribed reality." And Frank is said to sort of come back and said, "But the fashion you speak of was invented by you in 1905. To which, Einstein responds, and I just love this, "A good joke should not be repeated too often." Anyway, it's during this period that Einstein began to throw around the phrase, "God does not play dice with the universe," or some version of that, in letters and conversations with all sorts of people. In fact, he'd use it so often that at one point, Bohr would say, "Einstein, stop telling God what to do," right? Now, to be clear, in none of these instances does it seem that Einstein is making some sort of strong theological statement, as some seem to claim from time to time. As we've said in previous episodes, Einstein's spirituality was never something that became anything really formal. If anything, he seemed to believe that if there was some sort of a deity, that being would be a lot like the sort of design organizing principles of a rational universe as conceived by the philosopher Baruch Spinoza, who argued for strict causality and overarching elegance in his expression of mathematical laws. The God in the quote, therefore, if and when it was uttered by Einstein in a more serious vein, was in fact the universe. A universe that Einstein believed deep down in his bones was in fact deterministic. In time, though, as evidence and arguments for the role of indeterminacy and probability in atomic processes piled up and became nearly irrefutable, Einstein would be forced to concede that the picture of quantum theory was correct insofar as it went. However, he would come to assert instead that even if it was not incorrect, it was incomplete. That there were underlying physical laws or processes that were heretofore undiscovered that gave rise to the seemingly probabilistic behaviors. This quote-unquote hidden variable hypothesis said that there were, as of yet undetected ways in which a system or an object interacted with, or, for lack of a better term, communicated with the environment. Since these interactions were not as of yet observable, the results due to them would look as if they occurred in one way in a certain percentage of circumstances and in a different way in another certain percentage of circumstances. It's an amazing shift over the course of about 25 years for Einstein, going from being a person who's willing to throw out absolute space and time to being a person who is not willing to let go of strict determinism. And I have a feeling that Mach would have had some strong words for Einstein on the matter had the two men talked about it after about 1925 or so. So, if Einstein was so dubious of quantum theory, what was he working on during the period of the 1920s and early 1930s? The most scientifically notable thing is another one of those sort of really ironic bits of Einstein history. In 1924, he received a paper from a young Indian theoretical physicist by the name of Satyendra Nath Bose. The paper took Einstein's work of deriving Planck's black-body radiation law using statistics and reworked it with a new assumption. And that was, if two particles were identical in terms of their type and energy, they would actually be indistinguishable. And so, in terms of how you did the statistical counting, well, you couldn't treat them as two separate things. They had to be treated as the same thing. And so let me see if I can explain that, because that's really sort of a strange idea. Now, if you think about a deck of cards, every single card in the deck is unique, and so the statistics of understanding the various probabilities of getting a certain combination of cards has to take that uniqueness of each card into account. However, if you think of rolling dice, the dice might not be thought of as having that same uniqueness. If you roll 2 dice, there are a lot of different ways you can come up with a roll of 7. Now, if one die is red in color and the other is blue, you can tell there's a difference between a red 3 and a blue 4, and a red 4 and a blue 3. They both add up to 7, but you can tell that the dice are different. On the other hand, if you were to roll 2 green dice, you can't really tell which die is which, especially if you were to do it, say, like in a closed box and then just open the box up. And so the 2, 3, 4 states will look to be identical to each other. What Bose showed was that if this was the case in a real physical system, say electrons, or I shouldn't say electrons really, but say photons in a gas, one couldn't count these states as being 2 different states in a system. You had to actually count them as only just being one state. Now this was amazing to Einstein, and he decided to sort of run with the idea. And the outcome of that was that he not only got Bose's original paper published, which was something that was really pretty amazing in Central European journals at the time because they were pretty closed off to anybody outside of their little fraternity, but he then extended Bose's work with 3 papers of his own that showed, by the end of all the work, that particles that could do this could form an interesting state of matter that allowed them to behave collectively if the particles that made up that matter could all be in the same quantum state. And this state of matter is what's known as a Bose-Einstein Condensate. And it would become the basis of understanding such bizarre things as superfluids, where you take something like liquid helium and you cool it down to a certain point, and then all of a sudden it no longer has any viscosity, and if you stir it, it goes around forever and does all sorts of weird things. Or the phenomena such as substances becoming superconductors at low enough temperatures. He also pushed forward the ideas that de Broglie and Schrödinger came up with, using wave dynamics to describe the behavior of particles such as electrons. In this, Einstein developed tests to show that what might be called traditional matter is also subject to wave-particle duality, kind of like we talked about earlier, and by doing that, proved additional evidence for the very ideas that he was often in resistance to. Max Born later wrote, quote, "Einstein is thereby clearly involved in the foundation of wave mechanics, and no alibi can disprove it." End quote. By and large, though, the majority of Einstein's time, from about 1918, 1919 on, was spent working on what are now known as unified or grand unified field theories. So what are these? Well, we've talked a lot about how James Clerk Maxwell, in the 1860s, developed a mathematical model of electromagnetism that described the physical phenomena as an interaction of particles in something known as a field. Einstein used a similar approach to rewrite gravitation with his general theory of relativity. What he wanted to do was find a way to unify these two descriptions as a single complete theory. It was very much a continuation of his lifelong desire to take similar but separate physical phenomena and create descriptions of them that stem from the same physical principles. It was and is something that almost all of the great figures in physics in the 20th and even now into the 21st century have tried to do. We've discussed Eddington's attempts in this series, as well as Heisenberg's and Pauli's attempts in our series on the history of the atom. For Einstein, the way forward seemed to be through an extension of the mathematical program that led him to success with general relativity. In this, he hoped not only to unify these two interactions, but also to find his hidden variables that would explain what was going on in quantum mechanics, and maybe even resolve what interactions were taking place in the nuclei of atoms. Now, I'm not even going to attempt to get into the weeds of the actual work here for two reasons. First, it involves an extension of the already super complicated math needed to do general relativity. Second, it turned out, all of it, to be a lot of tilting at windmills in many ways. What I do want to do, however, is comment on what was taking place around all of this. What I think is most notable is how each paper he published and each pronouncement he made regarding this work was seized upon not so much by his colleagues, though they were certainly interested, but by the popular media. On multiple occasions, papers like the New York Times ran breathless headlines proclaiming that Einstein had come up with a quote-unquote new theory of everything, only for the hype to fade once others had reviewed the work and raised issues with it. It really was an early case of poor science communication by an over-enthusiastic media looking for sensationalism. Listeners of this podcast who read a lot of science stories written for popular consumption today will recognize the phenomenon, and it's really during this period of time that originates. Another departure is that Einstein seems to have almost completely abandoned his physical intuition regarding the systems in this pursuit. To a degree, this is really pretty understandable. It's really hard to have any intuitive physical sense of things going on in four-dimensional or higher spaces as would take place when Einstein built on the work of mathematician Oscar Klein. He had tried to make physical considerations preeminent in his derivation of general relativity, and that had, to a degree, led him astray. And it was only once he returned to the mathematical program that he got back on track in that area of research. So his decision to follow the mathematics and to sort of see where that led or guided him is pretty understandable. The problem was, as would be the case with so many of these efforts by all the different people who tried them, was that without the sense of a physical understanding to anchor them, the theories often produced outcomes that, when examined, suggested somewhat absurd consequences. While it's easy to armchair quarterback some of this stuff, especially in light of the work done in the 50s, 60s, and 70s on renormalization and unification around gauge theories, I think that there's a real sense that had Einstein and others pushed a little bit harder to tie what they were doing, back to some sort of a physical touchstone. In other words, to do a better job of relating, physical systems to theory and vice versa, things would have gone a lot better. Finally, it's important to realize that even though Einstein didn't succeed in this quest, neither has anyone else really. At the time, men like Heisenberg, Pauli, and Dirac were working on ways to quantize Maxwell's electromagnetic field theory, while, as we've said, Einstein, Eddington, and Erwin Schrödinger would be working to try to unify gravity and electromagnetism along more classical lines. Additionally, physicists such as Bohr, Enrico Fermi, and Hideki Yukawa would have some success in developing classical sorts of models for the interactions between subatomic particles found in the atomic nucleus. While Dirac would succeed in integrating relativistic effects into quantum theory, thereby generalizing Schrödinger's wave equations, no one from that pre-Second World War generation had any other success. It wouldn't be until the work of Feynman, Schwinger, and Tominaga that workable quantum field theories would be developed for electromagnetism, the weak nuclear force, and the strong nuclear force, with Steven Weinberg showing how the first two could be unified in high-energy conditions. However, even with this progress, gravitation has remained stubbornly ununifiable. It doesn't seem to be able to be quantized, nor does it seem to sort of fit with the other interactions in the standard model of particle physics. While some have suggested that Einstein's drop-off in meaningful production after his papers in the mid-1920s is evidence of a loss of a certain edge or insight, I think that misses the mark somewhat. As I've said, it's not like any of the other best minds in physics or cosmology have done any better at unifying gravitation with other interactions in the 100 or so years since Einstein first started trying. Moreover, as we'll talk about in future episodes, it's not as if Einstein stopped contributing altogether. His continued dialogue with Bohr, something that physicist John Wheeler has characterized in writing by saying, quote, "In all the history of human thought, there is no greater dialogue than that which took place over the years between Niels Bohr and Albert Einstein about the meaning of the quantum," end quote. It's this ongoing conversation, something that, by the way, we discuss in our episodes 2.25.2, or 1 and 2, I should say, that, force the rest of the physics community to really think long and hard about the nature of reality. In that way, working as much as a philosopher of physics as he did working as a physicist, Einstein's contributions resonate clear through until today, as there are still experiments being conducted to test his various, thought experiments. Finally, as we'll discuss in the next couple of episodes, by 1932, Europe had once again begun to unravel politically. This time, however, it wouldn't be over some nationalistic sense of who was the greatest nation, but instead over much more pernicious ideological issues, centered around which form of government was best and the issue of race. These forces would disrupt both the scientific community at large and Einstein personally in such a way that made scientific progress significantly more difficult, especially once the war of ideas transformed into a war of flesh and blood and earth and steel. However, in the 15 years or so between the end of the Great War and the rise of Hitler to power in Germany, Einstein lived an increasingly bourgeois life with solid heavy furniture and comfortable German foods. His marriage to Elsa settled into something profoundly domestic, even while he conducted a series of affairs with various mistresses more or less discreetly. As he turned 50, he was the greatest physicist alive, even as some of his colleagues considered him a bit of a relic due to his intransigence on the quantum question. As a gift to himself, he and Elsa bought a piece of land in a small town known as Kaputh on the outskirts of Potsdam, and had a house built on the edge of the lake there. It was an idyllic place where he'd get away from the crowds and the press, and he could guide his sailboat across the water while thinking about the nature of the universe. It would be during this time that he would heal his relationship to Mileva to some degree. Once the pain of the end of their marriage had subsided, and they had both gained a little distance and perspective, they remembered what had attracted them to each other in the first place. And while in this case there was never any hint of any sort of rekindling of the passion they had once shared, they did find much in each other's intellects and senses of humor to find a way to spend some time together beyond the necessities required by their two boys. As for the two children, Einstein's relationship with them was difficult. That's a good way to put it, I think. His relationship with his oldest son, Hans Albert, would be a roller coaster, in part for the same reasons he and his mother had quarreled over Mileva. Hans had fallen in love with an older woman whom his father did not approve, and so there was a seemingly continuous back and forth and up and down in their letters and visits that kept the two from ever growing truly close to each other. Einstein's other son, Edward, was intelligent, sensitive, but emotionally and mentally troubled. For a time he studied to be a doctor and then a psychologist, but over the years he spiraled into bipolar disorder and schizophrenia. He would spend much of his adult life institutionalized, often at his own request, and at one point attempted suicide. As his condition worsened, his father would reach out through letters and music to try to bring him back to some level of stability, but to no avail. In time, his connection to his first family would be severed as political developments forced him to flee Europe forever. This brings us to a good place to conclude this episode of the podcast. Our shout out this week goes to the fine listeners in the Twin Cities of Minneapolis and St. Paul, there on the banks of the upper Mississippi River. I have to admit that I've never had a chance to visit that area of the country, but I find much to admire about your history of unity through diversity. For those of you up there, if you've got a moment to drop us a line here at the Scientific Odyssey, either through our Facebook group, at our website, thescientificodyssey.typepad.com, or at my Twitter handle, @ChadDavies, and let us know what scientific wonders that are there up there on the banks of the mighty Mississippi, we'd really love to see that. And, let's do this. Let's say that goes for everyone else as well. Here in the States, as I record this, we're rapidly approaching the unofficial beginning of the summer of 2018, which is Memorial Day. And what that means, at least around here, and I think probably for most of everybody, at least in the Northern Hemisphere, and that is that a lot of folks are going to be traveling here pretty soon. So if you get a chance to see some cool science stuff, why not snap a picture of your adventure and upload it to that Facebook page? Let us see your geologic formations, your scientific institutions, your amazing landscapes, your really cool instruments, your sunsets and sunrises, and everything else that you might see. I think it'd be awesome to have a summer of science that we could all sort of look back to and marvel at. On my part, look for a few more things to start appearing there from the crew here at the Scientific Odyssey as well, and let's see if we can get something started that we can all enjoy. Before we sign off, let me also, once again, just give a huge thanks to the folks at the Blue Dot Sessions for their wonderful compositions. The sessions have done a lot of music for a lot of different podcasts, and we're thankful here at the Scientific Odyssey that they've been kind enough to allow us to use their music to add some atmosphere to our navigations. All of the compositions for this episode, by the way, are off their most recent release known as Contours, or titled Contours. If you'd like to hear more, you can head over to their website, sessions.blue, that's BLUE, and listen to a whole lot more material that they have out there. Next time, we'll follow the life of Einstein as he goes into permanent exile, and by doing so, changes the course of science in the United States. Until then, full sails on your journey.